For inviting me to this event. So I have the pleasure of co-leading the Functional Materials and Microsystems Research Group at RMIT University. I've been in Melbourne for over nearly 17 years now, but I'm actually originally from Chennai. So it's a pleasure to, start my year presenting to a conference which is actually based out in Chennai. I would have loved to have to do this in person, but then as we all know, the pandemic prevents a lot of things from happening. This, in a snapshot, is what our group does. So our group is actually quite broad in the sense we don't really focus on one particular thing. We work on quite a few different things, which include the stretchable and the wearable sensors, which I'll be talking about today in detail. We also work on ultra-thin novel materials, so which is more like 2D materials. We also work on brain mimicking devices, so artificial brain mimicking devices, and on devices which work for the optical and terahertz applications. The common thing which connects all these different applications is we mainly use inorganic materials, predominantly oxides and chalcogenides, and mostly in the form of thin films to connect all these applications together. I don't lead this team by myself. Well, we are three people leading the team together, and that kind of allows us to, diversify into so many different applications. So I've kind of divided up my talk into a few different sections. So I'll do the first section now, which is using stretchable oxides and generating electronic devices using that. It's kind of a very different kind of a problem. So this is not something which most people would think of doing because stretchable materials are very different to oxide materials. But this was the motivation for us when we started doing this work back in 2012. So we've been doing this for nearly 8 or 9 years right now. And our main motivation at that point was we didn't want to create and generate a new class of materials for stretchable electronics. We thought electronics has come a long way, they behave beautifully. Why can't we just take the materials which make current electronics and try and render them stretchable? For those of you who work on oxide materials, you will know they usually are deposited at high temperatures. They are extremely brittle in nature, whereas the stretchable materials are usually the opposite. They don't withstand high temperatures and they're extremely mechanically pliable and flexible. So what we wanted to do was come up with a technique which allows us to combine two very, very different materials. So we started using silicone rubber or PDMS as the stretchable substrate. And our initial test case was indium tin oxide. And then we then diversified into using other oxide materials using the same technique. The next two slides will kind of give you an idea of the transfer process which we actually developed within the group. So this was a process which was then patented, and then that's led on to other studies and also led into some industry collaborations. So the entire premise on which this transfer process works is the fact that platinum does not stick to silicon. So if you use platinum with silicon, you generally use an adhesion layer. But in this case, we didn't want the platinum to stick well to the silicon because we're using the platinum as a transfer layer. So we put down the platinum thin film on silicon, but let it adhere quite poorly. Now, because we're still working off on silicon, we can deposit any oxide at any high temperature using the standard techniques and then pattern it using the standard techniques, either photolithography or using nanofabrication techniques. So what you see over there in figure C is basically the indium tin oxide patterned on top of the platinum sitting on top of silicon. Now we spin coat and cure PDMS or the silicone rubber on top of this and we peel it off. And when we peel it off, what essentially happens is because the platinum is not stuck very well to the silicon, the entire layer just comes off along with the oxide underneath it, along with the PDMS. So when you flip it, you basically have the platinum, the oxide layer, and then the PDMS. We get rid of the platinum layer using reactive ion etching. And now you have your device, which is your indium tin oxide sitting within the PDMS. Now, it's a beautiful process because we can use it again and again. We can use it for nano pattern films, for micro pattern films. The adhesion is really good because the oxide is kind of semi-embedded inside the polymer. You can get excellent resolution as this image over here shows you, and you can do large areas. We've done up to 4-inch silicon wafers, and you can get the 100% transfer rate over a very large area. So we thought, okay, we managed to transfer the indium tin oxide onto PDMS. Now, generally, indium tin oxide, like any other oxide, is brittle. So it will not withstand anything beyond, say, 3 or 4% of strain. So we strain these to see what exactly happens to the resistance parameters. Surprisingly, it behaved okay up to almost around 12% of strain. And then beyond 15%, it kind of went open circuit. But once you let it go and went back to its original 0% strain, it kind of recovered its resistance properties. So you're quite surprised to see this happen. We did a number of cycles. These were very initial results from 2013, but since then, the performance has been significantly ramped up. And we were trying to understand how is it that indium tin oxide, which is extremely brittle, actually now is able to withstand strain up to around 12%. Now, the beauty behind this was the fact that we put this in a scanning electron microscope, and we found that the oxide layer is no longer a continuous thin film. What you see over there is kind of overlapping plate structure. So it's no longer a thin film, it's not cracked, but instead what you have is an overlapping plate structure. Now that's really, really unique, because what that allows it to do is when you stretch it, the plates slide on top of each other. And as long as the strain value is still allowing electrical connectivity between the plates, it is still behaving normally. But then beyond that, it cracks kind of appear. But once you let go, it again goes back and slides on top of each other. So we call this a microtectonic effect because it's a bit similar to the tectonic plates which make up the Earth's crust. But it's this effect which actually allows the oxides to be stretched up to around 12% or 15%. We thought, great, we managed to get this working. We managed to take indium tin oxide and make it work on PDMS. What if we try other oxide layers or other oxide devices? So we tried the same process with zinc oxide, and exactly same process, nothing really changed except for the fact it's now zinc oxide deposited by sputtering. And we realized that you could do the same process again. Nothing, it still works as a transfer process for zinc oxide on PDMS devices. Now, using this, we demonstrated a couple of applications. So we tried demonstrating gas sensors using zinc oxide. Now, typically, if you work with gas sensors, you would know gas sensors don't really work at room temperature. You need to actually heat them up to around, say, 150 or 200 degrees centigrade to get them working. The amazing fact was these were gas sensors which actually work at room temperature. So even at room temperature, you're able to actually sense and pick up the difference in the gases. So they are resistive sensors. So the resistance of the material changes based on the gas they're actually being subject to. So here you can see it is sensing hydrogen and nitrogen dioxide differently. And even with strain, it continues to sense these two gases. Now, zinc oxide is also a very nice UV sensor material. So we use this to also demonstrate some UV sensors. So as you can see over here, again, the sensitivity is really, really high. And what really lends the sensitivity to be that high is the fact that because it has this microtectonic structure, the surface area is extremely high. And so any enhanced surface area generally leads to better sensitivity. So higher the surface roughness, higher the surface area, and the better sensitivity, which is what we see in these particular cases. So this was pretty much what we were at around 2015, 2016. And we thought it's pretty exciting because we have sensors which are thin, they're transparent, you can put them on your skin, and you can actually use them in the future as wearable sensors. So that kind of led to a few industry partnerships. I'll kind of touch on a few industry partnerships towards the end of my talk, but it was pretty interesting and to have a versatile process. So you could use any oxide and make it into any kind of a sensor which you want to make it into. So it was a very exciting time to actually have these results back in 2016 and then go and talk to a variety of industry partners. I'll kind of move slightly to the side and talk a little bit about optical devices which could also be enabled by the same transfer process. So in this particular case, we were actually looking at exactly the same transfer process, but in this case, we were using titanium dioxide. Now, titanium dioxide is a wonderful refractive index material, which is used very commonly for optical applications. And in this case, the titanium dioxide or PDMS, you have a very nice refractive index contrast. Now, generally, you could never obviously take an oxide material and put it on a stretchable substrate and make, various applications out of it. So given that we have this process, we were able to make these titanium dioxide devices, which we used to demonstrate some tunable grating type applications. So you can see we used electron beam lithography and we generated these little circles of titanium dioxide sitting on top of the PDMS. So as we stretch the device, you can actually change the diffraction patterns which you get out of these particular devices. So it's quite nice to use these as a tunable grating type devices. So you can see as you change the strain which you're applying on your titanium dioxide device, you're measuring a change in the diffraction pattern, which in turn relates to the amount of strain being applied. So it's quite nice to create these kind of patterns by actually just merely stretching the device and thereby lend the tunability to your optical devices. And another interesting factor which we found was we actually did some finite element modeling with this, and we found that actually the fact that you have little discs of titanium dioxide sitting in the PDMS, it's the PDMS which basically absorbs all the strain. So the silicone rubber is basically absorbing all the strain, and the little discs of titanium dioxide are almost mechanically invisible. So because they don't see the strain as much, that's the main reason you're able to again strain these to up to around 20% and still keep reusing these devices without any kind of issues, which you would not be able to do if you just had a standard layer of titanium dioxide sitting on top as a thin film. So we use red laser light, green laser light, and we did the typical experiments where we tried and compared the analytical modeling results and the finite element modeling results. And we applied strain on the device and also measured the strain and tried and see how we could actually use these for various tunable grating type applications. What was even more fascinating by doing this is we reached out to our collaborators at University of Adelaide. Now, we've worked with them for quite a long time on terahertz and optical devices. And they said, this is really fascinating because we could use these to actually make meta surfaces which are actually tunable. So meta surfaces are basically subwavelength resonant elements which interact with light, and thereby you can change the way the entire material is interacting with the light, and it changes its properties based on the way it interacts with it. Now, generally, you could never really use these kind of materials in them. Normally use metals to make meta surfaces, but obviously metals have very high loss, and so efficiency becomes a problem. The other key thing which you would like to have meta surfaces to have is tunability. And this, the fact that it sits on PDMS offers mechanical tunable options for these dielectric resonators. So we designed these devices were designed at Adelaide, and they basically found that if you can change the polarization of the light, which is actually impinging on the sample, and change the strain which is being applied on the material, you can actually switch the optical resonance of your sample. So you can either get a red shift in your optical resonance or a green shift in your optical resonance, just based on the amount of strain you're applying on the sample and by changing the polarization of the light which you're exciting the sample with. So what you see on this slide are essentially the simulation results, but then we fabricated these, and what you see on this slide is actually the experimental results, which kind of prove the simulation results almost exactly. So you can see the red shift and the green shift happening with the Y or X polarized light, and strain is basically causing the changes in the optical resonance. So this is a pretty exciting thing for in the world of meta surfaces and in the world of optics. We hope to be able to explore more of this. So most recently, we were awarded an ARC Center of Excellence. So that's actually an Australian Research Council Center of Excellence. It's a massive program. So it's a 7-year program which runs across multiple organizations in Australia as well as internationally. And the entire focus on this is actually transformative meta-optical systems. So what we hope to do over the next 7 years is to be able to generate light at the nanoscale, manipulate the light, and also detect light at the nanoscale. So kind of almost bring about the next optical revolution in the world of optics and create an array of optical devices which could be used for various applications. So as it's a brand new center, we are still recruiting PhD candidates and postdocs. So if that's something interested in joining us, do check out tmos.org.au. We normally would have progressed much faster, but obviously the pandemic has, caused a lot of things to go much slower than what we would like it to go. So do check out the website and to understand and learn more about this particular center. I'll move on to the third part of my talk, which is on oxides for electronic skin. Now, this is very, very recent work which we carried out in our group. And the fact that we actually work on various topics, so the fact that we work on brain mimicking electronics and we also work on wearable and oxides and wearable sensors, kind of allows us to work at the junction between these two very, very different areas. So one of the fantastic postdocs in our group, he actually came up with this idea of thinking, we have 3 very different sets of results. How about bringing all 3 together and actually creating electronic skin, or rather skin which kind of mimics the way in which the actual human skin behaves? One of the main elements which we use in this electronic skin, besides the sensing part of things, is the fact that we have the brain mimicking electronics sitting along with the sensor. So for those of you who are not very familiar with this, there's a field of memristors. So memristors are actually the fourth missing element in the electronics. So you have the resistors, the inductors, and the capacitors. The memristors was always considered to be the fourth missing element. So where the resistance characteristics of the material actually depends on, it remembers the previous voltage states. So it's kind of resistors which have memory, which is why you call it memristors. But it's very, very similar to the way our brain behaves. So you can almost imagine the synaptic gap between two neurons to be very similar to the way the memristor behaves. So memristor has two metal electrodes and the oxide layer sitting between them. That's exactly mimicking the way our synaptic gap in our body behaves. So the fact that you could use these memristors to mimic brain functionality is what we put to use to create our electronic skin. So what we tried mimicking in this particular case was we're trying to create a system which actually takes in real stimuli. So we're not mimicking the stimulus, we're actually applying real pressure and we're applying real temperature. And we're trying to see and mimic how our skin actually reacts to those kind of external stimuli. So we have mimicked various aspects of the skin, and those are what I'll be showing you in the next few slides. So the first thing which we mimicked is the Pacinian corpuscle. If you look at your fingers, you'll actually see that you have all of us have these on our fingers. It's basically sensing pressure. So we mimicked this using a pressure sensor using gold and PDMS, which we connected up to our to our brain mimicking device. In this case, it's a strontium titanate enabled memristor component. And connecting these two across each other kind of mimics the entire way in which our body actually reacts to pressure. So we don't react to every kind of pressure which our skin faces. We only react to stimuli which, kind of increases or goes beyond a particular threshold. So only when the pressure is high, the memristor component is constantly comparing the external pressure to what it needs to react to. And then you start seeing an actual signal or response signal which is coming out of our body. So that's the Pacinian corpuscle being mimicked using pressure sensors and memristors. The second thing which our skin does quite often is it has thermoreceptors all over the body. So thermoreceptors are essentially that you're constantly checking for thermal stimuli. So any changes in temperature and beyond a particular temperature, our brain obviously signals to our body to move away from the particular stimulus. To say you're touching something hot, if it's not too hot, you don't react to it. But if it exceeds a particular temperature, then our brain sends a signal and says, move away from it, it's dangerous for you. That's essentially what we're mimicking in this particular case. So we use vanadium oxide, which is a fantastic material because it changes its electronic properties based on external temperature. It's not just a temperature sensor, it's actually an insulator to metal transition material. So it dramatically changes its electronic properties, and that is what we put to use in this particular thermoreceptor application. So what you see over here is nothing happens until you hit the transition point for the vanadium dioxide, which is around 68 degrees centigrade. And at that point, instantly the memristor circuit kicks in and starts behaving like the brain would behave and kind of sends off those signals to tell you that it's too high and you need to move away from it. The third thing which we also mimicked is the nociceptor behavior. Now, this is probably the most difficult thing to mimic because it is not just a mere comparison of external stimuli versus we know how our brain is reacting. It's also trying to mimic the sensitivity of the skin. So we don't, sometimes people suffer from neuropathy diseases where, your skin might be hypersensitive or it might be sensitive to even very, very low stimuli. Those are typically states which you call allodynia and hyperalgesia. So if you see in this graph over here, allodynia is basically where you start reacting to even stimuli which you don't normally start reacting to. And hyperalgesia is the state where your response is extremely high, even beyond what is normal. So using the vanadium dioxide in combination with the memristor, that's what lends the non-linearity in this behavior. We were actually able to mimic the allodynia and hyperalgesia behavior of the electronic skin. Now, why is this important? This study is particularly important because it allows you or gives you the ability to actually sense pain. So because you're using the sensors along with the brain mimicking electronics, you're kind of almost mimicking exactly the way our body behaves. So you can kind of almost sense everything which you're supposed to sense in terms of comparison with a threshold. So the fact that you can control this threshold and the fact that actually this mimics the sensation of pain makes this really, really special. So in the future, we kind of see this as skin which could be integrated with prosthetics. So to make the prosthetic arm more like a human arm. Last 3 slides, I'll just talk a little bit about my industry partnered projects. We've been incredibly lucky to work with almost 7 or 8 different industry partners in parallel. There was a stage in the middle where nothing really went anywhere. I took nearly 40 to 50 meetings and nothing really eventuated in terms of partnerships. But then things turned around for us after around 2018, 2019, and a lot of our industry partnerships kind of started happening from that point. I think as an engineer, as an innovator, this is something which really, really excites me, because the fact that you can make or have fundamental research being done in the lab, get good results, and then actually see that being commercialized in partnership with industry is something which is extremely exciting. So just 3 examples. The first one is we are working with a company called Nutromics. And the idea behind what Nutromics would like to do is kind of create a personalized diet and a health patch. So this is a patch which is stuck onto your skin. It's constantly sensing biomarkers in the interstitial fluid in your body, and you're trying to constantly keep looking out for spikes in your glucose levels. So what you're trying to do is prevent the early onset of diabetes and also get an understanding of what you eat, how that controls or spikes up your glucose levels. So having a patch which is constantly monitoring this and constantly giving you that feedback information hopefully allows us to start eating healthier and start having better understanding of how our diet controls our health. So this is something which we've been doing for the last year or so, and there's a lot of technology integration, the miniaturization of the electronics. All this is things which we partner with Nutromics in doing. A second example is, again, a patch which is applied onto the skin, but this has a very different intention. So this is particularly with a company called Blepis, who wanted to use this patch for aged care health and infection intervention. So imagine having this patch being put on people in the aged care centers or residential aged care facilities, and it's constantly monitoring their oxygen levels, their ECG, and their skin temperature. And that way, any person who's actually looking after these people gets that instant information and gets those triggers at which you need to start giving them medical attention. So again, this is something we've been doing for a year and trying to make sure that we can do the sensor development and the wireless electronics side by side along with each other is something which is exciting. The third project was actually one of our earliest industry partnered projects, and it's actually probably the biggest of the lot, in the sense this is actually not micro or nano anymore. We're looking at sensors to actually deploy across an entire mattress. So this is where we're trying to have smart bedding for aged care monitoring and support. So sensors which can be deployed across an entire mattress to provide non-invasive monitoring of people in residential aged care facility, in due course of time, not just measuring whether the person is in bed or not in bed, but also measuring if there are changes in their breathing rate or changes in their heart rate, which allows the person who's taking care of them to instantly be there overnight and provide the level of support. This was probably the most challenging so far, because it's been 3 years since we started this project. The upscaling of our technology to mattress size has been significantly challenging, and also understand and keeping the low cost, but at the same time keeping the reliability of the data really high. These are the typical challenges which we work through in this particular project. It's an exciting time though, because we're actually going to field trials later this year, and we are really excited to see actually this hitting the market hopefully relatively soon. Before I finish up, all the things which I spoke about today, it's not me personally standing in the lab and executing them. It's a fantastic team of young researchers, postdocs, and PhD students motivated and who have worked hard through the many, many years delivering this. This was our last team photograph, which we took back in 2019. No prizes for guessing why we couldn't do this in 2020, but hopefully we can all meet face to face quite soon and start having these exciting conversations again. And a big thank you to obviously all the funding partners without whom we wouldn't actually be here, for funding both the fundamental aspects of the research as well as the industry collaborations in the last few years. And that is me. So thank you very much. I could take questions now if anybody has any questions.
Yeah, okay. Sorry, it was on mute. So thank you, Professor Bhaskaran, for a wonderful talk, and also a lot of applied sciences and technology involved in it. So now time is up for short discussions. There are some questions in the chat box. Let me repeat. 1 minute. Yeah, there was someone, Santos. Can you raise your question now? Okay, there was one question. It was in bandgap tuning, stretching in uniaxial way leads nowhere as force cancel out in the other axis. So what we, let me see. It's not coming the full question as such. Who is raising the question? Santosh.
Santosh.
He's not here.
Uh,
The next one, can you tell the next one?
Sure.
so the one question is, the refractive index will be changed depend upon the film thickness.
It depends more on the film properties. So for instance, if you take titanium dioxide, if it's rutile phase or anatase phase, then that controls the refractive index more than just the film thickness. So in this particular case, we had to be very careful in making sure that we get the right phase of the material by controlling the way in which it's deposited and the way and the temperature at which it's being annealed.
The other question raised by Kalayarazan. Kalayarazan is there. So the question is, in bandgap tuning, stretching in uniaxial way leads nowhere as force cancel out in the other axis. So what we see here is uniaxial, So uniaxial stretching to tune in photonics, how is differ in these two cases?
I'm guessing this relates more to the X and Y polarized light and the dielectric resonators. I'm guessing it applies more to that. I don't get the specific question, but I'm happy to, for the person to reach out to me and then have a further discussion if that makes sense.
Kalayarazan, are you here? I think he's not.
It's not here actually.
That's okay. So happy for them to reach out to me over email and then we can have a further discussion.
All of you can mail directly to Prasad. Actually, the email ID is also already there, so you can directly reach out to her. So with this, let us thank again Professor Madhu Bhaskaran for a wonderful talk. So next, let's back to our CL, contributory lectures. The